This video is about basics of fields as they are presented at the undergraduate level, and it's by no means meant to be exhaustive. However, you may consider it as a crash course on basics of fields. There will be some gaps, some unintentional, some may be intentional, hoping that they will be good exercise for you to cover. Now, this is what the main topic revolves around: field extensions. And field extensions are a special case of ring extensions, which is defined to be this. So we have two rings. I will refer to R as sometimes as the base ring and S as the over ring. They share the same identity. Here's an important tool whose use is ubiquitous in field theory. This is called the evaluation map. It's presented here in a more general setting, namely that of the ring extension R and S, where A is an element of S that commutes with all elements of R. Then the map phi that takes each polynomial to its value at the point A is a ring homomorphism. It's nice to know that it's a ring homomorphism, which is something that you should verify at least once. And its image is denoted like this. Now RA, sometimes I'll refer to it as RA, sometimes as the extension of R in S by A. This is at the same time the smallest subring of S containing R and A. Okay, let's go back to our focus now, the field extensions. So you take an element A of the over field E, then FA is an integral domain sitting inside the field E, and the question that drives the whole discussion that we will carry out is this: when is FA a field? To find it out, at least to characterize this situation, we start out by assuming it is a field and maybe hope to get some necessary conditions, expecting at some point them to build up to a body of sufficient conditions as well. So you start out assuming it's a field. What that means for the evaluation map is that it is non-zero. It has non-zero kernel, because if it had zero kernel, then FA would be isomorphic to, ring isomorphic to this polynomial ring over F in one indeterminate, which is not a field but just a PID, principal ideal domain. So if it's a field, then the kernel must be non-zero. What that is equivalent to is that there is a non-zero polynomial in Fx that has A as its root, as one of its roots. In this situation, we say A is algebraic over F. Okay, now let's make that a starting point of the next discussion. Suppose A is algebraic over F. That is equivalent to kernel phi being a non-zero ideal of the PID Fx. And that means it is generated by a non-zero element and a non-zero and non-unit element, say F. Now, we further claim that F is irreducible. That means it's a non-zero, non-unit element of the domain Fx, which never decomposes into the product of two non-unit elements. So we will assume F is equal to G times H and try to prove that one of them is a unit, namely in this case a constant polynomial that is non-zero. Okay, if this is so, then you can evaluate both sides of this equality at the point A, and since f of A is 0, then the product of G of A and H of A is 0 too. That's because phi is a homomorphism, ring homomorphism, that factors over products as well as sums. Okay, so let's say G GA, since we're working in a domain, let's say it is g of a that's 0. This puts g, the polynomial g, in the kernel of phi. But the kernel is generated by f, therefore at f divides pi, f divides g, which in turn divides f because of this equality. So what happens in a domain when this is the situation? This makes the other factor in the product, namely h, a unit, which in this case is a constant polynomial. So that proves f is irreducible in the PID fx, and being as such, the ideal generated by f, namely the kernel of phi, is a maximal ideal of the principal ideal domain fx. And being a maximal ideal, its factor with respect to the kernel, the factor of fx with respect to the kernel, is a field, but that's by isomorphism theorems, it's isomorphic to fa. So we have just established that the algebraicity of the element A is equivalent to fa being a field. Now, let's delve a little deeper into the situation when fa is a field. If this is the case, let's going back to adopting the previous assumption, namely that kernel phi is generated by the element f. Let's say f is a polynomial to the degree n. What happens in this situation is that if you take any element of the fx, let's say t, you can apply the division algorithm to get a quotient, to divide t by f and get a quotient q and the remainder r, which is either 0 or has smaller degree than that of f. Okay? Then, once again, if you evaluate both sides of this equality at the point A, you get t of a equal to r of a. Since r's degree is less than that of, if it's either 0 or its degree is less than that of f, that puts t of a right in this subspace, right? This is a f subspace of the field E. And we have just showed that every element of fa is here. The converse is also clear because every element here can be realized as the value of a polynomial of degree at most n minus 1 over f, evaluated at a, right? So the equality should now be clear. Now this only shows that the elements the powers of a from the 0th power through the n minus 1st power generate fa as a vector subspace of E, containing f, of course. Note that. In fact, we claim a little more than that, actually much more than that. We claim that this is a basis for the vector space fa. Let's see that it's a basis. Take a linear combination of all these powers of a through the 0 from the 0th to the n minus 1st power that is assumed to be equal to 0. Okay? And consider the polynomial obtained by replacing a by x. That's the polynomial that's divisible by f, because it's a polynomial that has a as its root, and all such polynomials, the ideal of all such polynomials is generated by f. They are multiples of f. But, okay, now f is a polynomial of degree n, which now divides a polynomial of degree n minus 1. That goes to show that this ladder polynomial has to be 0. But for a polynomial with these coefficients to be 0 means all coefficients are 0. That establishes that these elements are actually independent, linearly independent. And now, combining with what we obtained here, the equality that is, it makes up a basis, this set makes up a basis for the vector space Fa. If in this situation that we've just worked out, if you take, instead of just any generator of the kernel F, a monic generator, then there's only one such element in kernel F. There may be several generators, but only one monic generator. So then we will call that monic generator the minimum polynomial of A over F, and it's denoted like this. And we've just worked out to show, we've just verified that its degree is equal to the dimension of F as a vector space. So we have verified this equality. From now on, we will mostly use this notation for denoting the degree of a vector space, the dimension of a vector space E over a subspace F, over the base field. Okay. So we have established what so far? If Fa is a field, then the degree of Fa over F as an F vector space is finite. We actually said more than that, but we're going to take this as a starting point to see if this is enough to yield this condition. That is, it is enough to yield this condition. So let's assume that the degree of Fa as a vector space over F is finite. So is this sufficient to guarantee that Fa is a field? All we have to do to verify this is take a non-zero element from Fa, call it R, and see if the left multiplication by R is F linear. It's easy to verify, and 1 to 1 because we are in a domain, and being a linear transformation between these two vector spaces, I mean the linear transformation on the vector space Fa, that is, the image of the dimension of the image is equal to the dimension of Fa. Now, but this guy also sits as a subspace of Fa, therefore we have the equality, proving that every element R is invertible, therefore Fa is a field, except the zero element, of course. Okay. Let us summarize all we have discussed so far in a theorem. Well, the next part of the discussion will be a separate video. Hope to see you there. Thank you.